This is applied physics for an undergraduate and graduate students, and this is the first lecture. It is on measurements and standards. I am Dr. Nasir Mirza, and I will be talking about the applied physics. The textbook in this regard is Physics Volume 1. Fifth or higher edition can be used. It is from Resnick, Halliday, and Crane. We start with the physical quantities, standards, and units. We know very well that measurements are basically used to describe natural phenomena, and every measurement is associated with a physical quantity. We want to measure length, we want to measure mass, we want to measure time, period. We would like to see how the time is progressing and what kind of force is being applied. So, measurements are associated with physical quantities. We need to define standards, and standards are really needed for the measurements and the repetition of the experiments. When we want to repeat an experiment, or we would like to offer somebody that you can do this experiment again, then there must be some standard against which the measurements must be done. It should also be readily available and accessible, and the experimentation should be possible, and measurements should be possible anywhere around the world. Well, we must also quantify things and processes so that some properties that can be measured with high confidence and also with the minimum error. The measurements do carry the possibility of error or precision, and then we need to work on that. We must yield same results when the experiments are repeated by somebody else, anywhere, by anybody. The results must be same. And also, whatever the results are obtained, they must not change with time. If the results start changing with time, then those results are no more reliable. And physical quantities and standards must be such that the measured values must remain independent of the effect of the time. Well, there are fundamental quantities, and then there are derived quantities. The fundamental quantities include the length, time, mass, the amount, the temperature, the current, or many other quantities. And the derived quantities are like speed, like force, momentum, or impact, or the rotational momentum, things that are really derived from these basic quantities that contain length and mass and time. International systems of units were defined after deliberations, and they were termed as a Standard International. In France, such activity took place. People from the globe got together there and established international standards and international system of units, and was called Standard International. They are based on 7 quantities and also given a metric system name. Before we go further into the system, we must refresh our memory about the some basic ideas, and this includes the prefixes for magnitudes, and also the Greek alphabets that we are going to use in physics again and again. So let us refresh our memory about the magnitudes and the prefixes for magnitudes and Greek letters. The prefixes for magnitude include these factors: the deca, hecto, kilo, mega, uh, giga, tera, and peta. The frequently employed factor of kilo we see among many cases, and kilograms, the amount is famous for purchasing things, and this half a kilogram or quarter of a kilogram or 2 kilograms or 100 kilograms are really used. So the kilo is a prefix and K is the notation. Similarly, mega is a prefix, megawatt of electric power. So mega is 10 to the power 6. Giga is 10 to the power 9, and is employed in many cases in computers. The gigabytes are termed as a giga is a prefix of 10 to the power 9. Similarly, tera, tera is 10 to the power 12. 12 is a very large number, and terabytes we know is a memory size which is available in current these memory cards, where the terabytes are frequently being employed. Similarly, peta is 10 to the power 15, and it must not be confused with the bread, the pita bread. It is not that small. 10 to the power 15 is a very, very large number, and it is a prefix for magnitude. We can write the output in typical electric power plant as 1.3 into 10 to the power 9 watts, or 1.3 gigawatts, or sometimes in the abbreviated form it is written as 1.3 gigawatt. Similarly, we can write the time interval often encountered in nuclear physics as 2.35 into 10 to the power minus 9 seconds. So 10 to the power minus 9 is the nano, and so it's 2.35 nanoseconds, and sometimes abbreviated form it is written as 2.35 nanoseconds. The kilogram is SI based unit, and already we know that it contains a prefix of kilo. 10 to the power 3 kg is not expressed as a kilogram. Again, repetition is not done. Instead, 10 to the power 3 kg is a megagram, and it is also written as 1 ton. So if we look at the factors that are very small factors, deci is 1 over 10, and 1 over 100 is centimeter. I'm sorry, the centi is the prefix and the meter is the unit. So centimeters are for length, 1 over 100 of a meter. Milli, 10 to the power minus 3. The micro is 10 to the power minus 6. Nano is 10 to the power minus 9. And pico is 10 to the power minus 12. Femto is a very, very small magnitude. 10 to the power minus 15 is the prefix, and F is used for this purpose. For micro, this mu is employed. This is a Greek word, and the rest of the symbols are in English. Let's briefly look into the Greek alphabets. Here we see the small letters, the alpha and the beta and the gamma and the delta, and so the capital alpha, capital beta, capital gamma, and capital delta, and so on. Let's go through some difficult names as well. We are going to use frequently in physics many of these Greek letters again and again. We recall this pi. The pi is employed in as radius or the perimeter of a circle. Let's go through this Greek alphabet once again. The alpha, the beta, gamma, delta, epsilon, zeta, eta, and theta. Theta is generally employed in physics for angles. Similarly, iota, in mathematics, it is symbol for under root -1. Kappa, lambda, we have seen lambda in many cases in waves where the lambda is the wavelength. Mu, nu is employed for the frequency in physics. Xi, omicron, pi value, rho for the density, sigma for the in physics cross section, the macroscopic and microscopic sigma, tau, the value of tau for in many cases for time, very special times, epsilon, phi. Phi is generally employed for the flux, the intensity, or the number of particles per unit area. Chi, again psi, omega, the capital omega and the small omega. It is generally used for the angular frequency in physics. We will use them again and again, and we will see how the Greek letters are really part of the vocabulary of physics. Now we come back to the physical quantities again in physics, and the physical variables and the categories. The basic categories are length, the time, the mass, the amount of substance, and the current, and many others. And the derived categories include speed, acceleration, force, momentum. For example, this force is derived unit, and in SI it is Newton, abbreviated as capital N, and 1 Newton is 1 kg mass multiplied by the meters, the units of length, and it is not capital, it is a small letter, and S square, the meters per second square. So this is really the unit for the acceleration, and 1 Newton is 1 kg multiplied by the meters per second square. Power similarly is 1 watt, which is 1 Newton multiplied by the meters divided by the time, seconds. So 1 kg into meters per second square is the Newton, 1 Newton multiplied by meters per second, and that's the you can see that the units for the derived physical variable can be further reduced to the basic units, the kg, kilogram, and the meters and the seconds. So we see here that it is the kilogram meter square divided by second cube, as in the denominator second square, and the second appears. So another example, for 60 miles per hour to be converted into SI unit, the standard international units, 1 mile is roughly 1609 meters. And 1 hour can be written as 60 minutes, and 60 minutes can further be written into 60 seconds. So 3,600 seconds is the conversion for 1 hour. So speed can be written as 60 miles per hour multiplied by 1,609 meters per mile multiplied by 1 over 3,600 in terms of hours per second. So we cancel things here. We see here that the hour is cancelled with hour, miles are cancelled with miles, and we are left with the meters per second, and the numbers are multiplied and divided, and we reach at the result of 26.8 meters per second. It is very important to know that when you convert from one type of unit to another units, then you have to be watchful about the basic quantities like length, like time, like mass, they will appear eventually in the units. Let us see what are the SI based units for different basic quantities. The length is a basic quantity and its dimension is L, and SI unit name is meter, and SI unit symbol is M. The time has a dimension of T, and its SI unit name is second, and it is abbreviated as S. Mass has a capital M, and it is expressed in kilogram for SI units, and kg is the symbol employed for the SI unit symbol. Temperature is expressed generally in terms of theta, the Greek letter theta, and the SI unit name is Kelvin, and it is written as only K. No degree sign is shown on it. The electric current is I, capital I, and it is expressed in SI units as ampere, and ampere is written as capital A. So, if we compare the system of units, there are three popular. There are other systems, but we will confine ourselves to these three systems. The first is the SI or metric system. The other is CG as the centimeter, grams, and second systems. And then there is FTP systems, the foot pound system. And the units for the basic things, the length, the temperature, the mass, the time are following. The length is meters for metric system, and temperature is in Kelvin degrees, and the mass is expressed in kilograms, and the time is S, seconds. Similarly, in the CGS system, the centimeter is the unit for length, and degree centigrade is the temperature units, gram is the mass unit, and the time is expressed in seconds. The foot pound system, the British system, is having the foot, 1 foot as a length, and the temperature is expressed in the Fahrenheit degree, and the mass is expressed in the pound mass, and M is written for the mass notation, because there is a force also which is expressed as a pound force. So it is written as pound F or only pound. The time is expressed as S, the seconds, and the system of units are interchangeably used, but we will try to confine ourselves with the SI or metric systems. Let's now go through the standards for the basic units, and the first standard is the length, and the length is expressed in meters, and meters are basically 100 centimeter is equal to meter, or 1 centimeter is equal to 1 over 100 meter. You can write inch in terms of the centimeters, and it is worthwhile to remember that 1 inch is basically 2.54 centimeters. 1 foot is equal to 0.3048 meters. So it's 1/3 of a meter is 1 foot. 1 foot contains 12 inches. 1 meter is roughly 3.281 feet. But for all practical purposes, 1 inch equal to 2.5 centimeter is a good thing to remember. 1 yard is 0.9 meters. 1 mile is 1.6 kilometers, and 1 kilometer is 0.6 2 mile. But there is another very important unit in physics. We use this. It is 1 light year. 1 light year is basically the time taken, 1 year's time taken by light to travel a distance. So basically 1 light year is the distance which light keeps on traveling for a year, and the distance roughly is 10 to the power 16 meters. It's a very large distance. So the distant galaxies and the stars are really termed in terms of the this distance. Although this distance is written as light year, but it is never the time. It's written in terms of the time like thing, but it is the distance. It is the distance that light takes to travel 1 year. The meter is then currently defined as the length of the path that is traveled by the light in a vacuum during the time interval of 1 divided by 299,792,458, 1 part in this much number. And this number is basically the defining quantity for the velocity of light. So if you multiply this number with the 1 second, this much meter is traveled. So we define the meter from here. 1 over this much is the of a second is the length traveled by light. So people do this measurement that they start the light from a source switch on at time t is equal to 0, and then they measure the time, and the light travel exactly as a fraction of the this much distance, and then the distance traveled is measured, and then it is converted into the length of a meter. Some measured lengths in physics are very important, and very roughly we will go through these important quantities. The nucleus length, all these lengths are expressed in terms of the meters. Now we must recall that these majority of these things are measured and few are estimated, but physicists have done these measurements or estimation from one side or another. So theoretical explanation for values are given, and then the experimental determination has been done. So first, let me go through the very large thing, that is the distance to the farthest observed galaxies, which is 1.4 into 10 to the power 26 meters. So it's a very, very large value in terms of meters, because so many zeros are after 1.4 multiplied by after 4, so many zeros, well, 26 zeros. So it's 100 contains 2 zeros, and 1000 contains 3 zeros, and so on. So it's 26 zeros. So it's an incredibly large number. The Milky Way diameter is roughly 2 into 10 to the power 21 meters. The solar system's diameter is 10 to the power 13. And the Earth and the Sun distance is 1.5 into 10 to the power 11 meters. The Sun's diameter is approximately 1.2 into 10 to the power 9 meters. 10 to the power 9 meters. The Earth's diameter is 1.3 into 10 to the power 7 meters. And in ancient times, the first prediction of the Earth's diameter was done by Al-Biruni, and his calculations and measurements revealed that Earth is about 2.9 to 1.29 roughly into 10 to the power 7 meters in today's terms. The approximate value was determined while Al-Biruni was traveling to India through the current regions of Pakistan. If we look at the blue whale, its length is about 30 meters, and a very, very difficult animal, blue whale. and species incredibly large. The human beings are between 1 and 2 meters. And if we go to smaller level, the cells um, are of the order of 10 to the power minus 5 meters, and it is 0.1 roughly. If I multiply this with the zero point 0.1 and divide by 0.1, I get here 10 to the power minus 6. Look at this minus 5. If I multiply with 1 over 10, then I get here 6. So this is a 10 micrometer. It's about 10 micrometer, and a bacteria is roughly a micrometer. And the small viruses, the viruses like the recent well-detected COVID-19 viruses of the size of 2 into 10 to the power minus 8 meters. So it's even smaller than, I think it is a small number as compared to micro. So it's a less than micro. It's a 1 over 100 times the 200 times smaller. So DNA diameter is even smaller than the virus, small virus. 1/10 of the size of the virus is the DNA's diameter, and the atom even smaller than the DNA diameter. It is 10 to the power minus 11 meters. The angstrom is a unit which is 10 to the power minus 10 used for the atoms, and it is a fraction of the angstrom. Nucleus is the smallest measured length of the size of 10 to the power minus 15, and 10 to the power minus 15 is the femtometer. So it is very, very small length. A proton or a neutron or a nucleus of hydrogen atom has roughly dia of the order of 10 to the power minus 15 meters. So in physics, these very small things have been measured with a high accuracy, and very large distances have been observed and determined of the order of 10 to the power 26. Now, if I want to know how much is the order, so it's a 26 plus 15, because this is the smallest scale and this is the largest scale. So I must divide this number through the distance which is the largest possible. So the ratio of the largest distance to the radius of the nucleus is of the order of 10 to the power plus 41. So it's order of magnitude, the 41 order of magnitude is the variation scale available for the measured lengths in the universe. Again, I would like to point out that the Farth has observed quasars are of the order of 2 into 10 to the power plus 26. Remember, this kind of a notation is called scientific notation, in which E is employed as an exponent plus 26. It means 10 to the power 26. So whenever you find E into E plus 26, it is a scientific and notation, and it is written for the computer calculations as well, as E plus 26 is equal to 10 to the power 26. Similarly, Andromeda galaxy is of the distances of the order of 10 to the power 22, and the radius of our galaxy is of the order of 10 to the power 19. The distance of nearest star is 10 to the power 16. Now, all these meters can be expressed, the very large values can be expressed in terms of light year. We have seen the light year, and it's a conversion factor. So these values can be redefined in terms of the light here. And remember that the height of the Mount Everest is roughly 10 or 9 kilometers. This is 10 to the power 3 meters. 10 to the power 3 meters means kilometers, and so it's a 9 kilometer or 10 kilometers high from the sea level. Height of a person is roughly 1 to 2 meters, and the size of the atom is of the order of 10 to the power minus 11 meters. And these were values measured using X-rays. The X-rays diffraction in physics helps us to find out the size of atom, and typical sizes were determined. And similarly, radius of proton or radius of hydrogen nucleus is about 1 femtometer, 10 to the power minus 15 meters, and the scale is gigantic scale which has been employed. The first lecture ends here, and we stop here, and we will move further. In the coming lecture, I will talk more about the standards and the units, and then I will compare the dimensions and would like to comment on the accuracy or how the measurements are written. And therefore, I would like to talk about the significant figures as well in the coming lecture. We stop here, and thank you so much.